So let's do our old reliable favorite student, good old Anne. Please, blah, 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 blah. A golf ball is thrown horizontally. I usually tend to underline the word horizontally. And I might tend to draw a little picture somewhere. Now, I didn't, as I look at this, give you guys much room. You know what? There's kind of room over here to draw a little picture. There's the cliff. 94 meters high. And a horizontal velocity of 22. Soon as I do that, I'm saying to myself, I'm going to break this up into horizontal and vertical with a little t-table, and I know that AX equals 0, AY equals negative 9.8, VX equals 22, VY initial equals 0. Oh, I need one more thing. DY equals negative 94. Now I can solve for t. I can solve for t vertically, because that's the column that I know 3 pieces of information in. It's a little easier if they give it to me horizontally, but that's okay. I think we ended up going with d equals VIT plus a half AT squared, but it's vertical, vertical, vertical. Conveniently, Matt. Woohoo! I think we ended up with t equaling the square root of 2 times dy all over a, I think, because we said times by 2, divide by a. How do you get rid of a squared square root? And I think it's going to end up being 2 times negative 94 over negative 9.8 square root. It's going to end up being 2 times negative 94 divided by negative 9.8 square root. Do you get 4.38 seconds? 4.4 seconds? I'll go to 4.38. 2 marks if you got that. Otherwise, I would give you 1 mark if I saw that, a half mark for the numbers, and a half mark for the answer. But if you've got the answer right, you get 2 out of 2. How far from the base of the cliff will the ball strike the ground? What's the fancy word for the horizontal displacement? Begins with the letter R. Range. I may use that on your test. Yes. They want dx, which is going to be vxt plus a half axt squared. However, Sean is bursting for me to say, hey, I don't need to write ax because ax is 0. In fact, horizontal range is a little easier. It's just going to be vxt. What was vx? 22. What was t? 4.38. Now, if you got 1a wrong, but you took your answer and you put it right there and you multiplied it by 22, you'll get full marks for 1b even though you got 1a wrong, because that's how I roll. So, oh, interruption, late student number 2. Meanwhile, 22 times 4, oh, I got this number on my calculator, times 22 is the range 96, technically 96 meters, 96.4 meters. I think to 2 sig figs technically, but 96.4 meters. Again, I would probably give you 1 mark for that, a half mark for that, and a half mark for the answer. C. What's the vertical velocity of the ball after 2.2 seconds? Okay, now, Hakeem, we have changed the situation. We're no longer talking about at the bottom, so I'm going to re-defic and list, and I'm going to, well, what's the word right before velocity that also begins with the letter V? I'm going to be thinking vertical, 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 vertical. So the first thing I'm going to write is, well, I know Vy initial is 0. I know Ay is negative 9.8. And they told me time is 2.2. And they want Vy final, not final when it hits the ground, Dylan, but final at 2.2 seconds. Oh, I can do this. This is going to be V final equals V initial plus At. It's going to be 0 plus negative 9.8 times 2.2. It's going to be negative 9.8 times 2.2, negative 21.6. What's the negative telling me? It's heading down. Meters per second. 1 mark, half mark, half mark. How far has the ball traveled horizontally? What's another word for the horizontal distance? This is the total range, but this is how far it's moved sideways at this point in free fall. It is going to be a dx, which is going to be a vxt, Jordan, and vx was still 22, but this time t is 2.2. You know what? It's moved 48.4 meters horizontally. 2 marks. How far has it fallen vertically? I could figure that out by using vertical. dy equals vyt plus a half ayt squared. I could find that out too, for that matter. I could tell you how far it had fallen from the cliff. But I chose not to. Number 2, a tennis ball is launched into the air at an angle of 33 degrees. Oh, angle. Here I did give you room to dulp. We have this. 26 meters per second, where this angle here is 33 degrees. Travels in an arc and it lands back on the ground again. It's launched from the ground to the ground. Tara, as soon as you give me angles, first thing I'm going to say is, you know what? I'm going to break this up into a horizontal and a vertical component, where this is opposite, hypotenuse, and adjacent, where sine 33 equals Vy over 26. Vy, we said, was sine, and we asked if there was some dumb, easy way to remember that Vy was sine, and I think I said to you, I got nothing. 26 sine 33, 14.2, which is what they want me to write here. So here, Vy equals 26 sine 33. If I see that, that gets you 1 mark. And I'm going to write 14.16, and then I'll round off to 3 sig figs. 14.16, which is 14.2 meters per second. I would give you 1 mark, and then 1 mark. If you said 14.16, though, Michael, I'm not being fussy on sig figs this year. Next year, sure. What's the initial horizontal velocity? Well, we said it turns out that cos 33 equals Vx over 26. Turns out Vx ended up being 26 cos 33. Cos 33, 21.8 meters per second. Again, 1 mark for the trig function, knowing that it was cos, 1 mark for the answer. How long is the tennis ball in the air for? Okay, now I'm going to tackle this, and I'm going to tackle this with my T-table approach. I got room over here. I'm going to say horizontally, AX is 0. AY vertically is negative 9.8. VX is 21.8. VY initial is not 0. It's 14.16. And that's not enough to do anything. What else do I know if I'm ending up back on the ground the same height as I started from? I heard, 16. Sorry, I missed all of that, but I think you were right. What's negative 14.16? YF. I think, I couldn't hear you. Vy final, is that what you said? So you're saying, hey, Mr. Dueck, what goes up must come down since we're ground to ground. I can only use that what goes up must come down if it's ground to ground, by the way. That's why off a cliff at an angle we save for physics 12, a little tougher. I agree with you, Matt, my friend. Vy final is negative 14.16, and aha! Now I have a column of two things I can find, sorry, I have three things, I can find the fourth. I'm going to solve for t vertically. I think I can use t equals v final minus v initial all over a. By the way, horizontally, what's the acceleration? Horizontally, what's the acceleration? 0. If I tried solving it horizontally and tried using horizontal, I'd be dividing by 0. Can you divide by 0? No, that's one of the reasons. Sorry, horizontal doesn't help me this time. But vertical sure does. And I'm not having to deal with square roots or anything like that. Kind of nice. It's going to be negative 14.16. Take away 14.16 divided by negative 9.8. Now, the other way you could do this is you could find the time to top by letting Vy be final be 0. And then doubling your time. Oh, by this time you know me. Come on. Yep, come on. You get 2.9 seconds? Yes? Did you find it, John? Because you've been looking for an awfully long time. No? Are you missing the quiz? You have the quiz in front of you? There you do? Okay. I don't know. 2.88 seconds. Yes? 2.9? How far down the field? Hey, that's the range. How do I find the range? Horizontal, horizontal, horizontal. Tara, I'm going to say D equals VIT plus a half AT squared, except it's horizontal, horizontal, horizontal. And Connor, my friend, what can you tell me about the horizontal acceleration? Thank you for coming through in the clutch. That really wasn't very clutch. I gave you a low ball, but thank you. So, Connor, if I hear you correctly, and I think I do, you're saying it's just going to be Vx times t. Vx was 21.8. T was 2.9. But I'll use the more accurate 2.8897 that I have stored on my calculator. In fact, if I really want it to be accurate, instead of using 21.8, I could say, hey, that was 26 cos 33, because that's really what Vx was. 63, 62.9, 63.1. I'm going to go 63 meters even. E, what's the maximum height reached by the tennis ball? Height, that's vertical, that's vertical, that's vertical. I think I can say Vy initial was 14.16. Ay is negative 9.8. Vy final is 0. D equals question mark. That's one way. Matt, the other way is you could have gone back to question C and you could have said, if you were sure that you had got question C right, divide that time by 2 and then use that to find a vertical distance. I just, whenever I can, if it's not too much trouble, avoid using an answer that I've calculated to find another answer that I've calculated. What I will often do to check my answer is go back and do it both ways before I hand the test in, then yay, I know I'm right. I'm going to go with D equals Vf squared minus Vi squared all over 2a. 0 squared minus 14.16 squared all over 2 times negative 9.8. 0 squared minus 14.16 squared all over 2 times negative 9.8. You get 10.2? No? Yes? The nods from the three of you that did the quiz? I don't know. Meters. Turn the page! Golf ball is launched horizontally from a cliff at 15.3 from a cliff, meters per second. Horizontally, I'd probably underline that word. It takes the ball 5.54 seconds to hit the ground. Oh, William, they gave me the time. That's going to make this question, I think, a lot easier. Tara, I'll dulp up here. All they've told me is this. They haven't given me any other displacements at all. I'll do my little T-chart. I think I can do it. I can fit it in right here. Tara, AX is 0, AY negative 9.8, right? I can write that right away. McKenna, VX is 15.3, yes? What's VY initial if we're launched horizontally? Trick question.
Did you say 0? You do correct. Yeah, it is 0. Give me like a heavy.
I only have two pieces of information. Now, normally we would say, I need a displacement or something. But what else did the question give me? What else did the question tell me? Time, and that can go in both columns because the time of flight horizontally is the same as the time of flight vertically. And suddenly I say to myself, I've got three things in each column. I can do whatever I want to. How high is the cliff? I can use dy equals vy initial t plus a half ay t squared. I can say, oh, you want the height? It's going to be, 0. Woohoo! 0.5 times negative 9.8 times 5.54 squared. It's going to be 0.5 times negative 9.8 times 5.54 squared. Now, that's giving me a displacement. You're ending up 150.4 meters below from where you started from. Generally, height, Sean, is a scalar. So if you said 150, I'm good. I'm going to write negative 150.4, and then I'll put an equal sign, and I'll say 150 meters as a height. Negative 100, how about the 1, Mr. Dueck? Negative 150.4 equals 150 meters high. 2 marks. What's the range of the golf ball? Why, that's a dx. That's going to be 15.3 times 5.54. 15.3 times 5.54. You get 84.8? 85 meters. What's the vertical velocity of the ball after 5.4 seconds? That's a Vy final, which is going to be a Vy initial plus Ayt. That's going to be a 0 plus negative 9.8 times 5.54. Negative 9.8 times 5.54. Negative 54.3 meters per second. What's the negative telling me? On the way down. Positive would mean on the way up, which couldn't happen if we launch Elijah horizontally, but next year when we launch from a cliff at an angle, so there's a vertical component, sure, it can be on the way up or on the way down. D. What's the resultant? By the way, I like question D. I like question D. I like question D. Question D is a nice question. What's the resultant velocity, magnitude, and direction of the golf ball after 5.54 seconds? Well, Dylan, as a picture, I think it's going to look like that. And I'll put an arrow on the end of it to make the vector clearer. And Elijah, what I'm going to realize is that that's actually broken up into a horizontal component with an arrow on the end of it, and William, a vertical component with an arrow on the end of it. And I know the horizontal component already. What's the horizontal component? What's the horizontal component throughout the entire flight of the projectile? 15.3, is that what I said? And the vertical at this moment, I just figured out in part C, it's 54.3. Nathan, what happened to the negative in front of the 54.3? I got an arrow. That's not, yeah, here you go. I can find the magnitude with Pythagoras. I'll call this V, how about R for resultant? It's going to be VR squared equals 15.3 squared plus 54.3 squared, and then I'm going to square root. The resultant magnitude is going to be 56.4? Yes? No? 1 mark for that. But I did say direction. Now the direction is going to be that angle theta right there. Lovely right angle. Riley, my friend, Vx, opposite, adjacent, or hypotenuse? Adjacent is correct. Yes, good. A, I heard you. Vy, opposite or hypotenuse? That's correct. Which trig function? What some of you did this weekend in the sun. So tan of mystery angle equals opposite over adjacent. I think the mystery angle is going to be shift tan of that. Opposite over adjacent. 74 degrees, 74.3. I'll go 74 degrees. So it's going to be at 74 degrees. I can't call that south of east because that is not north. How do I write this one? Do you remember? Below the horizontal, or if it was on its way up, which would be Physics 12 next year, above the horizontal. But this is going to be below the horizontal. And I would probably go 1 mark for that and 1 mark for the angle and the below the horizontal. Can you give yourself a score, please? Out of, holy smokes, 26. So, introduction to the theory of relativity. And we're going to start out looking at time. And we're going to do a thought experiment. Suppose we had a cannon that could launch a baseball at exactly 30 meters per second every time. Can you visualize it? Okay. Situation 1. Imagine that Sam is the target and he is holding a baseball glove and he's standing still. What would he see? Boom. He would see the baseball coming towards him. Yes? How fast would he see the baseball coming towards him? How fast would the baseball be traveling relative to Sam? Well, 30 meters per second. Nothing terribly profound there. Situation number 2, thought experiment number 2. Same situation as number 1, except this time the cannon is on the back of a pickup truck, and the truck is traveling towards Sam at 15 meters per second. What would Sam see? How fast would the baseball be traveling relative to Sam now if the cannon fires it at 30 meters per second, but the truck is already moving towards him at 15 meters per second? What would he see? 45 meters per second. By the way, the people on the truck, what would they see? To them, it would appear that the ball was simply traveling at 30 meters per second because their frame of reference is the truck. Yep. Situation number 3, same as situation number 1, except this time the cannon is on the back of the truck, but this time the truck is traveling away from Sam at 15 meters per second. What would Sam see? How fast would the baseball be traveling relative to Sam now? 15 meters per second. And this isn't that profound. This makes sense. I've seen this happen before. This is why when you throw something, if you take a running start, you throw it, it goes faster, not because you threw it faster, you added the momentum, of the speed of your run to it. This is why in football, Callum, they'll teach quarterbacks never to throw off their back foot fading, because by doing that, you've added a negative velocity component to the positive velocity of the ball. You're going to throw a duck. You're going to get picked off. Makes perfect sense until you go cosmic. So there is a famous experiment, the Michelson-Morley experiment. In the late 19th century, around 1880, 1890, two physicists, Michelson and Morley, they conducted an experiment. They thought they could do this same thing, except instead of Sam, they would make the Earth. Oh, and instead of the cannon firing baseball, the sun shooting its light towards us. Or actually, better yet, a distant star shooting its light towards us. And what they thought they could do is they could measure that 15 meters per second difference either way for a total of 30 meters per second difference. They thought they could measure it. They thought in January, when we were revolving around the sun, when we were moving towards the star, that should be the same as the pickup truck moving towards Sam. We should measure the speed of light to be a little bit bigger. The same way as Sam measured the baseball coming towards him at 45 meters per second. And they said, then we'll wait 6 months. It was a year-long experiment. When we're in July, when we're moving away from the star, you know what? We should find that the speed of light is a little bit slower. Because just the same way when the truck was moving away from Sam, even though the cannon was still firing it at 30, even though the star was still firing the light out at the speed of light, it would be 30 minus 15, 30, speed of light minus whatever speed the Earth was moving away from the star. Makes perfect sense. Makes common sense. Totally should be able to do that. But they didn't. So understand that the experiment, McKenna, they figured the same baseball thing that I just did with you, but we're going to use the Earth and a star. We're going to do it cosmically. So here is the picture. This is what they were trying to do. In January, the Earth was moving toward the star with the speed, let's call it u, relative to the sun. The speed of light relative to the sun was assumed to be, we usually use the letter c for the speed of light. So they thought when we were moving towards that star, we should measure c plus u. 30 plus 15. And then they thought that when we're moving away, we should get c minus u. But here's the bizarre thing. The expected result didn't materialize. Instead, they got the same answer for the speed of light both times. That would be as though you got the same answer for both of these situations. Say what? There was only one conclusion. Hakeem, light is special, and the speed of light is a constant. The speed of light itself never changes. So, wait a minute, Mr. Dueck. How can the speed of light never change in that situation? So the Michelson-Morley experiment is famous for its negative result. It's one of the most famous, oops, we didn't get the answer that we thought, experiments in history. It showed experimentally that the speed of light in space in a vacuum is the same for all observers, regardless of their velocity or the velocity of the source of the light. Whether we have the pickup truck moving away or towards, or whether we have Sam running towards or running away, if we're talking about light, you get the same answer no matter what. The speed of light simply does not depend on your frame of reference at all. No evidence could be found that space could be used as a fixed frame of reference. And this is why this is called the theory of relativity. You may have noticed up here I talked about relative to Sam. It turns out every velocity is relative. The speed of light is the cosmic speed limit. It's the one that never changes. We all actually are moving relative to the speed of light. Short version, turn the page. The speed of light is a constant. What's the implication of that, Elijah, my friend? You want to sit up because this is going to rock your world, I'm telling you. If speed is distance over time, see the meters per second? Or better yet, since we're going cosmic, if speed is space over time, then how can we always have the same speed? How can this answer never change? The only way that that can be occurring, how can this answer never change, is if one of these guys changes depending on the situation. Space and time are not constant. Time does not move the same. Time is not measured the same for everybody, everywhere. Here's our thought experiment. Here was Einstein's thought experiment. He said, consider the following situation. Suppose we have a spaceship that is emitting a flash of light. We're going to use the flash of light as our timer. But instead of sound, light. Situation number one. We're going to do very similar to the baseball cannon, but we're going to go cosmic. A spaceship is hovering at rest. So here's our little rocket ship. It's hovering at rest relative to the Earth, and it's going to send brief, regularly spaced flashes of light to the planet, like this picture here. Some time will elapse before the flashes get to the planet. It takes light for a while to travel that distance. Just as 8 minutes elapse before the sunlight gets to the Earth. So we're going to set this up so that we're going to send a flash every 6 minutes. Blink, 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 blink every 6 minutes. And this person here on the Earth will see a flash every 6 minutes because they are at rest relative to each other. So if I'm sending out a flash every 6 minutes, in 60 minutes, the ship will send out how many flashes? Do the math. 10. And in 60 minutes, the Earth will see how many flashes? Now we get weird and cool. Situation number two. When motion is involved, the situation is quite different. Now, it's important to note the speed of the flashes will still be c, the speed of light. Our symbol for the speed of light is the letter c for constant. No matter how much the ship or the receiver may move, they prove that you'll still measure the speed of light as the same answer. How frequently the flashes are seen, however, depends on the relative motion. When the ship travels toward the receiver, like in the picture below, the receiver is going to see the flashes more frequently. Why? Well, this happens not only because time is altered due to motion, but also because each following or succeeding flash has less of a distance to travel. So, suppose this spaceship emits a flash every 6 minutes. On the Earth, because this spaceship is moving to the right, which means it's traveling some distance before it releases the next flash, which means that next flash has less distance to travel, even though the spaceship on their clock is sending flashes every 6 minutes, on the Earth, they would be seeing flashes every 3 minutes. In 60 minutes, the ship will emit 10 flashes every 6 minutes. The Earth will receive 10 flashes, but they're going to be 3 minutes apart. How long will it take the Earth to receive those 10 flashes that, as far as the ship knows, took 60 minutes to send? 30 minutes. Now, replace the word flashes with a clock moving. On the ship, the same clock would have moved an hour. On the Earth, the same clock would have moved for 30 minutes. Time is not the same in different locations if you're moving. The universe is weird. Let's move away from the Earth. Let's move away from the Earth. Well, now what's happening as you move away from the Earth, Perry, those flashes of light have a further distance to travel. They're going to take longer to get to the Earth. Even though on the ship, every 6 minutes, I'm sending my flashes of light. Every 6 minutes, I'm sending my flashes of light. On the Earth, I see the flash every 12 minutes. What does that mean? If two events are separated by 6 minutes, according to the spaceship's clock, on the Earth, they'll be seen to be separated by 12 minutes when the spaceship is heading away from the Earth, and only 3 minutes when the ship is approaching. This leads us to what's called the twin paradox. The twin paradox says, hey, what if you had two twins born at the same time, and you put one on a fast-moving spaceship, and you left one on the Earth? And the answer is they will now start to age at different rates relative to each other. So a dramatic illustration of time dilation, that's the fancy word for time changing, being not constant, is provided by identical twins. One an astronaut, let's call him TA for astronaut, who takes a high speed. By high speed, you've got to be getting fairly close to the speed of light, half the speed of light or more. Round-trip journey in the galaxy while the other twin stays home. Let's call it TH for twin home. When the traveling twin returns, he is younger than the stay-at-home twin. Really? How much younger depends on the relative speeds involved. Let's walk through it. Okay. On the spaceship, on the way out during the first hour, he sends a flash every 6 minutes. 1 hour has elapsed. But as they're heading away, the Earth sees the flash every 12 minutes. How long would 10 flashes take then? So, you know what? Let's go in minutes. I'm going to say 60 minutes have elapsed on the ship. 2 hours, how many minutes? 120. Okay. On the way back, it's sending a flash every 6 minutes. It would still, at the beginning, receive some flashes at 12-minute intervals. But then, here, 60 minutes of time for the spaceship would end up being 30 minutes of time, for a total of 150 minutes versus 120 minutes. The twin has lived for 120 minutes on the spaceship, but his brother at home has lived for 30 minutes longer. Now, if you extend that over years, that's going to make a difference. Time has passed more slowly on the spaceship relative to the Earth. Okay? Let's fill this out together. And then at the end, this will be the end of the lesson, and you can work on the review. You ready? So when we're heading away, we see the flash every 12 minutes. So the first flash would appear on the Earth at 12:12, even though 12:06 was the time on the spaceship. The spaceship sends the next flash at 12:12 every 6 minutes, but it doesn't arrive on the Earth until 12 minutes later on the Earth. What's 12 minutes later than 12:12? 12:24. The spaceship sends another flash 6 minutes later. So what's 6 minutes later than 12:12? 12:18. But they don't get to the Earth. It's every 12 minutes. What time will it look like on the Earth? 12 what? 36. Let's keep going. on the spaceship, the next flash will be at what time? (12:24). But on Earth, you're not going to see that next flash until what time? 12:48. The next flash is going to be 6 minutes later, 12:30. On Earth, what time is it? You know what? Let's go to do the math easier. Let's go military time. Let's call it 1300 hours, which is 1 p.m. 6 minutes later, (12 minutes later), right? 6 minutes later, 12 minutes later. Zoom in so you can see this a bit better. 6 minutes later. By the way, there are equations where you can get these. We'll look at those next class. But for now, I'm walking you through the flashing method, the dot, dot, dot method. 12 minutes later. Right?
You went from 36 to 40.
I went 36 to 40? Oh, I've been bad math here? How about 12:42? Is that what you're saying? And then 12:48? Is that what you're saying? Thank you. Can't add by 6, apparently. 12:54? 13, add 12 minutes, 48, yes? And we get to 1 p.m. or 1300 hours. But over here, we're at 1400 hours. Now we're going to start heading back. We're going to turn around, we're going to head back. When we head back, so it's going to be another 6 minutes on the spaceship. It's going to be 13:06. But when we're approaching the Earth, we see, when the ship is coming back towards the Earth, now we don't see the flashes of light every 12 minutes. We see the flashes of light every 3 minutes. So what was the last time on the Earth? Was 1400 hours. Now we're going to see a flash of light 3 minutes later. 14:03. Now a lot of people think, oh, now the Earth is catching up, and so the times will match again when the spaceship gets back. They won't. 6 minutes. 3 minutes. 6 minutes. 3 minutes. 13:18, Mr. Dueck? Good gosh. Can't do math in my head today. Now it'd be 13:24, yes? I was foreshadowing. 3 minutes. 6 minutes. 3 minutes. 6 minutes. 3 minutes. 6 minutes. 3 minutes. 6 minutes. 3 minutes. Hey, let's keep filling this in. In fact, I'll fill in the rest of the column here. So add 6, Mr. Dueck. It's going to be 13:54. Then it's going to be 1400 hours, or 2 p.m. Add 3. It's going to be 14:27. 14. So he's arrived back home. He's meeting up with his brother, but will their watches have the same values? Nope. The twin that went a-traveling, his watch will say a half an hour more time passed relative to his brother. Oh, sorry, no, the Earth will be, the right-hand column is the Earth. The Earth, the twin on the Earth, his watch will have an extra half hour of time on it. Why? Because time is relative. The speed of light being constant demands that to keep it constant, something else in the equation has to change in the d equals vt. Yeah, the t does. That's how the v stays the same. Weird, but cool. Oh, and the faster you travel, the bigger this time dilation. And in fact, as soon as you start to walk about 15 decimal places in, you're already changing. Time is slowing down for you. Not that you'll notice. But when we put very sensitive atomic clocks on the fastest jet fighters and sent them around the Earth a couple of times, and we synchronized one clock on the ground with the one that was in the plane before it went around, we did find after a couple of these, when they came back, yeah, they were no longer in sync. It is measurable. It is measurable. In fact, they have to take this into account for GPS. The GPS satellites that are orbiting the Earth are moving fairly fast. And the way they calculate your position is they use d equals vt. But because they're moving fairly fast, they have to take into account the fact that time has slowed down from them a little bit. If they didn't, your GPSs would be off by about 50 meters. So we have to use this. We have to take this into account. What's your homework? Nothing. Well, yeah, your homework is study for the test, do the review, and any other missing assignments, please. Oh, by the way, you can barely see it there. These are going to be the time dilation equations and the speed changing equations, but I'll give you those next lesson.